Okay, guys, welcome. Today we're going to talk about logarithms as they sort of come about by inverses of exponential functions. All right, so what I hope to be able to do for this video is to talk about how to use exponential functions, how to evaluate some simple logarithms. We'll talk about how to use logarithms to find inverses of specific functions, and we'll talk about how to find the number of digits in a positive number by using a common logarithm. Okay. Now, before we can talk about any of this stuff, I just want to sort of explain what happens if you have a number raised to an irrational number, right? So we've talked about if we have an exponent being a positive whole number or a negative whole number, and we've talked about fractional exponents as well. But what we haven't talked about is what happens if you have an irrational exponent. Okay, so this is just going to help sort of, so the purpose of this example, oops. So the purpose of this example is essentially just to show that exponentials are continuous. Are continuous. Okay, and then the idea is that if you wanted to find 7 to the square root of 2, one thing that you could do would be to plug this into a calculator, right? If you plug this into a calculator, then that would give you, so I'm going to do it right on the side here, we have a 7, and I would raise that to the square root, let me put parentheses here, so square root of 2, and the calculator gives me that this is roughly 15.6729, we'll say. All right, now if we look at the square root of 2 off to the side, the square root of 2 is roughly 1.414214. All right, and there's other stuff, but that's good enough. Now, if I were to raise 7 to just this sort of this approximated answer for square root of 2, I should get something pretty close to what I got in the calculator. And of course, if we do that, if I do 7 to the 1.414214, I see that I get essentially the same guess here, right? I get 15.6729, right? So essentially what we can do is, in order to approximate these irrational exponents, you can sort of take as many digits of what the value is for your irrational number, and so take as many digits as you want and apply that into your approximation, and it should remain fairly accurate. All right, so this is basically showing that we're sort of allowed to define these irrational exponents. Okay, so, and this is basically just going to summarize that, right? So if your exponent is an irrational number, then that number is basically approximated by numbers b to the r, where r is close to your x value. All right, so you have b to the x is close to b to the r. All right, and that's essentially saying that your exponential functions are continuous in this sort of way. Okay, now just as a reminder, these are all the properties for exponents that we've talked about. Now, we did cover this in a previous video, so I'm not going to spend a lot of time on it, but these are some of the properties that we'll need in this section. Okay, now when we talk about an exponential function, something like b to the x, then we typically call b the base, and we need b to not be equal to 1. We also need b to be greater than 0, right? And you can think about why these would be problems. If b were equal to 1, then you have 1 to the x, and 1 to any power is just 1. So in that case, you would actually have a line and not an exponential function. And if b is negative, then you have negative numbers raised to both even and odd powers, and you get sort of like this weird flip-flopping thing that's happening. So we don't want to deal with any of that stuff either. So we require that our base is always positive, and we don't want our base to be 1 either, right? And of course, your variable, sort of the defining feature in the exponential function, is that your variable is in the exponent. All right, and that sort of distinguishes this from a different type of function, right? So this is what we mean by an exponential function. Now, some properties for exponential functions. So the domain for any exponential function is a set of all real numbers. So you can plug in any real number and you will get a solution, right? Now, the range is a little bit different. The range is only the set of positive numbers, right? So you can't get a negative by plugging in any x value, and you can't get 0 either when you plug in any x value. All right, we'll look at an example of this in just a second. Now, if your b is greater than 1, right, it says that f is increasing function. This is for b greater than 1, if your base is something bigger than 1. If your base is between 0 and 1, remember, it has to be bigger than 0 and it can't be 1. So if b is between 0 and 1, that's when you have a decreasing function. Right, and then some other properties is that your exponential is very close to 0 if x becomes negative and your absolute value of x is large. So if you have a large negative number, your exponential is going to get close to 0, but never quite reach it. All right, now I want to do a quick example of this, just as a quick little demonstration. So for example, let's say if you have something like y equals 2 to the x, right? Well, if you were to plot this on a table, well, what's going to happen? Let's look at -2, -1, 0, 1, and 2. Well, if you plug in a -2, you have 2 to the -2, which is 1 over 2 squared, which is 1/4. Okay, if you have -1, you have 2 to the -1, which is a 1 over 2 to the first, which is just 1 over 2. Anything to the 0 power we said was 1, and then these are easy. Here's 2 to the first, which is just 2, and here's 2 squared, which is 4. So if we look at this on a graph, here's what we got. So we know that we have a point at -2, our y value is 1/4. So we have something sort of close to the axis there. When x is -1, we're at 1/2, so we're a little bit further up. But then here's when we start to pick up. At 0, we're at 1. At x equals 1, we're at y equals 2. And at x equals 2, we're at y equals 4. So we're going to get something sort of like this. Right? And again, you actually have an asymptote here, because no matter how negative you make your exponent, you're just going to make this 1 divided by a larger and larger number, right? So if you're taking 1 and you're dividing it by a large number, that's going to get close to 0, the more negative you make your exponent. Okay, so that's sort of a refresher on some exponents. Okay, now that's exactly what this table is describing here, right? So we're letting our function be f of x equals 2 to the x. Now, it turns out that if we were to find f inverse of x, right, and we were to switch the 2 columns in this table here, what we'd have is what's called a logarithm of base 2, right? So what this is essentially saying is that the inverse of an exponential is a logarithm. All right. So what we're going to start out with first is log base 2. All right. So if you have log base 2 of y equal x, this is equivalent to saying that 2 to the x is equal to y, right? Now, what happens here? 2 is the base of the log, and 2 is still the base of the exponential. Now, y is with the logarithm, but y is not with the exponential. Right? And then on the other hand, x is not with the log, but it is with the exponential. And that's sort of the defining feature, right? So in general, regardless of what your base is, you can say that log base a of x equaling y is equivalent to a to the y equaling x. All right. And I sort of switch the variables here, but the idea is that whatever's with the logarithm, so in this case, the x is with the logarithm, it's not with the exponential, right? And whatever is not with the log is with the exponential, right? And the base is still the base no matter what. Now, if you can understand this relationship, understand this going back and forth between logarithms and exponents, that's the most important part of understanding these logarithms, right? So if you can understand this going back and forth, that's sort of the whole key here. All right, so we're going to sort of look at a couple examples here. And essentially, this is going to allow us to evaluate logarithms. Because what's going to happen is if you have a logarithm, you can convert it to an exponential form, and then you just solve the exponential equation that you have. So let's look at an example of that. So in part A, we want to evaluate log base 2 of 8. Okay, well, if we want to find something in math and we don't know what it is, we usually call it x, right? Now, if we convert this to exponential form, I keep my base the same, so 2 is still my base. And now the thing that's not with my logarithm, which is the x, is now with my exponential. All right, and the thing that's with my log is now not with my exponential. All right, well, if these things are equivalent, well, then this is easy because this is what power of 2 gives you 8, right? And of course, 8 we could say is 2 to the third, right? So this, of course, allows us to say that x is equal to 3. All right, so we just wrote 8 as a power of 2 there, and that allowed us to do that. Now for part B, do a similar situation. We want to find log base 2 of 1 over 32. And again, we're going to call that x. So if we convert this, this is saying that 2 to the x is equal to 1 over 32. Well, can we write 1 over 32 as a power of 2? Well, sure, because we know that 2 to the 5th will give us 32, and then if we make that negative, that puts it downstairs. So now we can say that 2 to the x is 2 to the negative 5, so this allows us to say that x is negative 5. All right. Now again, since these are equivalent, this allows us to say that log base 2 of 8 is 3, and this allows us to say that log base 2 of 1 over 32 is x, which is negative 5. All right, so that's sort of how we can evaluate these logarithms. Okay, now of course, here's the other situation. Now here we want to find a number t such that if I do 1 over t minus 8 equals 5, what value of t makes that happen? Well, now here we can convert this to a log, right? So because the idea here is that I can't raise 2 to a power to give me 5, right? That can't happen. So here's where we would use logarithms. I can say that this is log base 2 of 5, and then that would give me 2 to the 1 over, or sorry, that would just give me 1 over t minus 8. All right, so now we can solve this by cross multiplying, and we're going to get 1 is equal to log base 2 of 5 times t minus 8. We can divide both sides by the log. We'll get 1 over log base 2 of 5 is equal to t minus 8. And therefore, t is 1 over log base 2 of 5 plus 8. Now we'll talk about how we can get this in terms of a calculator, but for now, we're just going to leave it just like this. So we're going to say it's 1 over log base 2 of 5 plus 8 for now. All right, and again, we'll talk in a future video how to make this a little bit more precise. Okay, so again, just as a reminder, we've only done log base 2 so far, but this holds in general, right? If you have log base b of y is equal to x, that's equivalent to saying that b to the x is equal to y. So again, base is still the base. Whatever is with the log is not with the exponent. Whatever is not with the log is with the exponent. All right, so let's evaluate a couple of these. So in part A, we want to find log base 10 of 1,000. Well, we'll say that that's equal to x, and we'll convert it. So this is 10 to the x is equal to 1,000. And of course, if you want to write 1,000 as a power of 10, that's 10 to the third. So that means that x is equal to 3. Okay. Part B, we have log base 7 of 49. We'll again say that that's equal to x. So 7 to the x is 49. And of course, 49, we can write as 7 squared. So this means that x is equal to 2. All right, for part C, we have log base 3 of 1 over 81. Again, we'll say that's equal to x. And if we convert that, that's 3 to the x is 1 over 81. Now, you can write 1 over 81 as a power of 3. If you raise it to the fourth, that will get you to 81. And if you make it negative, then that gets us to 1 over 81. All right, so we have 3 to the x is 3 to the negative 4. So then x must be negative 4. Now, part D is something that we have to be a little bit creative with, because part D, we want to find log base 5 of square root of 5 is equal to x. All right, now if you convert this, this is 5 to the x equals square root of 5. And if you think about it, what's our exponential form of a square root? That's a 1/2 power, right? So this, of course, allows us to say that x is 1/2. Right? So again, this just shows that if you understand that relationship between going back and forth between logarithmic and exponential form, a lot of these problems are fairly simple. Okay. Now, a couple properties that essentially follow from this is that log base b for any number b of 1 is 0, right? Why is that true? Well, if you convert this, this says that b to the 0 is equal to 1. And of course, that's true, right? If you raise anything to the 0 power, you get 1. And then, of course, the second one says that log base b of b, regardless of what b is always 1. And of course, if you convert that, that just says that b to the first is equal to b, which of course is also true. All right, so finally, if we talk about the inverse of an exponential function b to the x, then the inverse, f inverse, is done by taking a logarithm with base b, right? And of course, if you were to compose f and f inverse together here, you would get y or x, whichever one you're starting with, right? Okay, so let's look at another example of this. All right, so we're going to suppose that our f is 3 times 5 to the x minus 7. All right, we want to find f inverse. Okay, well, let's do it. We'll show that sort of this is how we get the inverse, right? So how do we find the inverse? Of course, we would first check that this is 1-to-1, but this will be 1-to-1. If you graph it, you will get something, let's see, so you should get something like this. All right, so it will be 1-to-1. So first we replace f of x with y, then we switch x and y, and then we solve for y. So of course the idea is first we'll divide by 3, and then we have 5 to the y minus 7. Now how do I get that exponent out of the way? Well, I use a logarithm, right? So if I convert this to logarithmic form, I have a log of base 5, base is still my base, of x over 3, and that's equal to y minus 7, right? So of course, last but not least, I would have that y is equal to log base 5 of x over 3 plus 7, once I solve for y. All right, so that's where you're seeing sort of the inverse come into play there. So that's sort of the idea. Okay. Now, what are some other properties that we have? Well, these are sort of like the cancellation properties or the inverse properties. All right, so the first one says that if we have b to the log of b of y equaling y, well, if we convert this to exponential form, this says that b to the y is equal to log base b of y, right? Well, wait a second, did I mess this up here? Oh, no. So the way that we want to do this is we want to say that let's see. So if I say that log base b of y is equal to some number and we call it x, right? Then that log base b of y equaling x means that b to the x is equal to y, right? So let's see, what am I missing here? I don't think that's the way I want to explain it either. Let's see. Let me come back to that one. So the log base b of x, the second one should be easier, and that might give me a better idea of how to do it. Okay, so we have log base b of b to the x is equal to x. And if we convert this to exponential form, this just says that b to the x is equal to b to the x, right? Which of course is true. All right, now I think I see what I'm doing wrong here, right? So if I want to convert this to logarithmic form, I need to say this is log base b of y, and that would give me log base b of y, right? Because I keep my base the base, the thing that's not with the exponent is with the log, and the thing that's with the exponent is not with the log. Okay, so that's what that's saying. Oops, sorry about that. Okay, so those are the sort of cancellation properties. And what's nice there is that that sort of allows you to get variables that you want by themselves, right? And that's a helpful tool. Now, one more logarithm that we need to talk about is what's called a common logarithm, right? So the last thing in this section, before we move on to the next one, is what's called a common logarithm. And that's if you see a logarithm with no base, right? So in other words, there's no base there. It's understood that there is a 10 for that base, right? And most of the time, it's written without that base there. So if you see that, that's what that means. All right, so that concludes this video on logarithms as inverses of exponential functions. I hope you enjoyed, and I will see you next time.